Test run. All right. Hello, everyone that's joining remotely. This is our sixth session in the afternoon session, the APAC friendly session. And we're very fortunate to have the BlockScience team joining us. I'm very excited because I've been reading a lot about the post that they had recently titled "The Cat's Out of the Bag," talking about content addressable transformers. And I think it's a lovely blueprint that at the very least, every other compute over data project can learn a lot from. And so we've got David, Kelsey, and Joshua from the BlockScience team. And I'll just go ahead and hand it over to Kelsey to give us a bit of an intro, and we'll let the rest of the team take it from there.
Wonderful, thank you, and thanks so much for having us. I'll let David bring up the slides.
Let me know when you can see that.
Lovely, thank you. So the guys are going to talk about content addressable transformers and what we've actually been doing on that part. I get to give the lovely introduction to BlockScience, but before that, we'll just flick to the next slide to show where we're headed. Thank you. So next slide. So what is BlockScience? I guess one thing that's unique about us is that we're a multidisciplinary research and development firm, and we're specifically interested in complex systems, and that's almost at the stage of mapping the system and asking the hard questions and addressing some of the hard problems before the actual just day-to-day or straightforward kind of software engineering front. So a lot of the research we do is primary research as a team, and then this has led to some open source software development as well. So people might be familiar with CAD, the computer-aided design software that BlockScience has built. And this was really around, solving some of our own problems as we embark on working on complex systems, specifically those in the Web3 space. Next slide, and I'll hand to David to speak about some of the things that we've worked on and why compute over data.
So BlockScience and Protocol Labs are no strangers to one another, and we put together a slide to sort of outline the work we've done. So these are some of the projects that we worked on. An engineer who unfortunately couldn't be here for this presentation, Danilo Bernardinelli. He's in Berlin right now at a conference, and time zones just aren't working across the four of us. So he was the lead engineer on most of these projects. And then, as Kelsey mentioned, Filecoin makes a lot of use of CAD, and BlockScience makes a lot of use in CAD for the work we've done with Filecoin. And I'd just like to call out that Joshua is one of the main developers responsible for the CAD product. And also we'll make these slides available at the bottom. This HackMD book is something that Danilo put together to provide some more information about these products for projects that anybody's interested in. And the links on these pages go into some more depth about some of these topics. And then sort of given who we are and sort of our relationships, why do we care about compute over data? I think Kelsey is by training an ethnographer, and I think it's important to call out that these aren't just technical problems that we're trying to solve; they're social problems as well. The systems that we're developing are effectively algorithmic policy-making systems that we need to make sure work transparently and reproducibly. So CATS was sort of started out with that in mind. So transparency is a decent operational definition of trustability. At least it's sort of the beginnings of it. And reproducibility is a decent operational definition for verifiability. So that's a large part of what we want to be able to to bring to these algorithmic policymaking systems. And then lastly, sort of our observation was it's kind of hard to do this in Web3, largely due to the lack of sort of fundamental primitives. And I think that both CATs and compute over data are share motivation in this regard. So with that introduction to BlockScience and sort of an overview, we want to introduce CATs. And I'll take it from a conceptual point of view and then pass it off to Josh, who will go through the instance of CATs that he has developed. So basically, we're looking at, what is transformation? Let's start with a noun. It's always a good place to start. So basically, a transformer takes an input and produces an output. And there's a desire that some value has been added along the way to make it all the processing that takes place worthwhile. So here we're showing a transforming element. We call it a node. It's divided up into pieces. There's a structural and a functional component. These can be further subdivided into plant and infrastructure on the structure side, process and infrafunction on the function side. These are pretty fuzzy boundaries between these things, and largely they're divide based on temporal characteristics. Infrastructure and infrafunction change slowly, and plant and process can change more quickly. There's a little definition at the bottom of this slide that sort of gives a good description of infrafunction, which I found useful. Basically, it provides functions that are things like protecting, providing, supporting, connecting, containing, including, that sort of thing. Comes from a book on in a more traditional traditional institutions. So given that's a transformer, what is then a CAT? So if you take transformer and add content addressability to it, you get some interesting properties. One of them is that in a decentralized system, location addressability doesn't really work. Works fine in centralized systems, but in decentralized systems, location is frequently not known. Or even if it is known, it may not be accessible, or it may not be convenient. There may be better places to get the stuff that you're looking for from. So we've given content addressability, and a big call out to IPFS. Provides this ability to name things in a content-based fashion very nicely. Can be used to provide all of the instructions necessary to build a transformer, and additionally specify the input data that we want to be transformed. So in this picture, we've got again that CAT node. Here we're calling it a processor. The function and the structure are there. And what's added in here is what we call a component we call a factory, that basically takes an order, and in that order are links to, through content IDs, the structure as code to build the structure this thing's going to run on, the function as code to build the functional elements of the CAT, and also the content address of the input data. The factory can take all of that information, create a processor, execute the function using the input data, and make output data, in which case the factory spits out this invoice, which is really nothing but the order that was requesting all of this to be done, and the content address of the output from it. Nice property of all of this is that it sort of has provenance built in. That as you put transformers together, the orders and the invoices sort of keep track of where things came from, how things were created, and where things go. So, you know, I love quotes, so I'm always going to have a slide with quotes on it. Why are we doing this? There's a guy, sort of one of the patrons of data-driven systems development, Edward Deming, has a quote: "Data are not taken from museum pieces; they're taken as a basis for doing something. If nothing is to be done with the data, there's no use in collecting it. The ultimate purpose for taking data is to provide the basis for action, some recommendation for action. The step intermediate between collecting the data and the action is prediction." So that's sort of what we're doing. We're not collecting data to stick it in a database. We're not collecting it to stick it even in a data lake. We're collecting it to make some product that's useful to people. And that idea was pushed by Chamak Degani. Excuse me if I totally butchered her name. I've never actually heard it. But she has this idea that she developed of a data mesh. And central to that is the purpose of functions within a data mesh are to produce these data products. And that the idea of sort of domain level responsibility for those data products is a key thing. I think I find it compatible both with what I've read in the compute over data literature I've gone through, and it's certainly central to CATS. So if people aren't familiar with it, I would advise that I would certainly recommend they take a look at some of her ideas. We've got a reference here. So given all that, sort of how do CATS and CODs, how do we put all this together? What do we want to get out of it? And just taking the idea of a data mesh and moving it into the decentralized space that we work in Web3, and looking at sort of the layering that's inherent in data mesh. We can have you need a data layer. The data has to be somewhere. There are technologies around that provide that. Things like file storage, Web3 storage provides that. Streaming, Ceramic Network provides that. So we've got our data layer. An action layer, you need to be able to process the data, or it's just sitting there for museum purposes, and we don't want that. So that's, I think, compute over data is producing tools for that processing, being able to process data in a decentralized system. And then we see CATS as sort of working in this domain layer, as providing the business logic that define what the products need to come out of these transformations need to be. So that's our sort of breakdown, and a lot of what we want to get out of the interaction with the compute over data work group is sort of validation. We've done this in a vacuum. What do other folks think about this as a layout? They have better ideas, different ideas, and then just being able to show CATS to a wider audience as well. So without further ado, that's the conceptual basis of what we're doing. Josh, do you want to take on the what you've done?
Sure. Next slide. Okay, so what is a CAT and why are they useful? Okay, CATS is a unified data processing framework for decentralized mesh network, for a decentralized mesh network to empower collaboration on products implemented with multi-cloud services that enable data provenance by content addressing the means of data transport between services. That's a wordy explanation of the sentence below the title. I felt as though I should connect them all. So in other words, they'll enable the creation of a Web3 service, self-service platform of data products as decentralized services deployed on mesh network pairs with data process verification using Web2 centralized multi-cloud services, software as a service, platform as a service, infrastructure as a service in multiple cloud service platforms, AWS, GCP, Azure, etc., right? All within this unified processing framework, right? The platform will empower the collaboration on products across domains between cross-functional and multidisciplinary teams and organizations, right? By reducing the operational overhead of adding new data sources via decentralized and distributing responsibility to those collaborating within bounded domains to support continuous change and scalability. In other words, if I use buzzwords to describe this kind of value, it's a multidisciplinary team working on a aspect of a product as a micro product deployed as a micro software as a service. So on the mesh network that we're envisioning, that the CAT software will be deployed on nodes of. The multidisciplinary team only has to focus on data sources they need without the operational overhead of procuring them within a centralized organization, right? So that's the value of CATS. It's a operational improvement, right, on using a mesh network, right? Next slide. Okay. So how are they useful specifically? The input, data transformation. Oh, sorry, CATS. Well, no, I'll wait for that one. Okay. They enable data process verification and transport between services with IPFS CIDs, which are the content addresses. All right. So those enable maintenance and reporting of data process provenance and data or process lineage as a result, because if you have data provenance, you get data lineage as a byproduct, which is a business intelligence view of data processes on the mesh, right? So they'll be used, each individual CAT, the IO of which would be chains of evidence that certify data process accuracy on the pipelines. So just to reword that, provenance is established in the API using retrievable CID record entries, which also contain CIDs, right? These record entries are input and output necessary to re-execute a deterministic process in a pipeline of post-processed, in a pipeline that has been post-processed, a pipeline of CATs. It's wordy, but I had to prove provenance this way with the IO itself, right? Because the input and output is used to re-execute a CAT. So that's a very important concept for the next slide. Cute. Okay. The input is everything on the left-hand side. Okay, it's the data itself, obviously, the transformation itself, and the infrastructure of code. The CIDs are generated by the CAT, right? By clients, IPFS clients on the worker nodes of a software as a service. In this case, it's Spark, which will also transform the input data, CID, that provenance record entry, right, to produce an output, which is a combination of another record entry and the result data. And as you can see, the cloud service model is encapsulated in a cat for which a multidisciplinary team collaborates on a single cat. Q. Okay. This is an example of David's slide above that's collapsed between the cat processor and the node. So the processor is software to be deployed on a single node. I thought that was important to mention. So you have structure, which is a user-specified computation or data transformation framework, such as Spark, Dask, etc. The software as a service. And you have infrastructure as code. In Cat's case, it's Terraform, right? This structure exists such that a function is executed upon it. And the function is a data transformation API, which I have an example in the next slide for, or some arbitrary computational process performed by the software as a service, in this case, Spark. So that computational process, or which would be a transformation in this case, would be a Spark data frame transformation, and the API would be Spark SQL, right? Which is the process. And the cat interface that isolates that transformation for the user experience is called the infra function. Okay, Q. This is an example of that isolation in the user experience, where one is using Spark SQL to transform a data set abstracted by a Spark data frame using Spark SQL. So I decided to have a combination of, like, ANSI SQL and just like Spark API, just to show you that, it's both. Okay. Q, next slide. All right. Could I take over here? Could I share my screen here?
Sure.
Okay. I have to run through this fast. Oh no. All right.
You're good.
Okay. Share screen. Okay, so I just want to explain the demo before I demo, okay? Just to tie it all together. So this, okay. I'm using kube control, okay, in order to monitor execution, right? This control plane, the service, the secret, identity and access management is in Terraform. For example, cluster role binding is handled by a PySpark API behind the hood that I'm using to build a Docker image that I've modified to include an IPFS client on, that will be pulled from Docker to be worker nodes of a Spark cluster. Okay, here's an example. In this example, there are two. So each of these Spark workers have an IPFS client that's being used as a storage hack, because we don't have Web3 storage, right, yet. But there's a cache. So once it's CID'd by the first cat, that cluster is non-ephemeral for the purposes of, because we don't have storage yet, right? And the second cat gets those CIDs of the data set and other URIs necessary to process itself, I guess. So I just needed to note that, right? And this is an example of, I would say, that record entry I referred to earlier. We're calling it like a bill of materials. It's a supply chain term that we still. So you have input transformation invoice, data output, all CID'd. The data output is partitioned in the case for distributed processing. Everything all the partitions are CID'd. So this is kind of like an example BOM, or that provenance record entry that is retrievable and re-executable from the IPFS network. So that's an input, right? So the first cat's purpose is to content identify the data set because it's not on the network and we don't have storage yet. Okay. This is an example of everything critical in the provenance record entry, or the BOM, necessary to execute a cat. In this case, it's creating input for the second one. These are the same. So it's like cat 0 produces the input for the subsequent cat. So this is the input for the subsequent cat. Spark transforms it. The IPFS clients, CIDs, everything necessary for re-executing both the input and the output. And then you have an output BOM. So the execution of the second cat produces an input BOM and an output BOM, everything necessary to re-execute the entire pipeline. To the demo. I don't have much time. Okay, I had to rush through that one. Okay. So I have, hold on, window. Okay, in this example, I have cat 0. Okay, let me share my entire screen. Hold on. Maybe a side by side. Okay, there. Okay. In this example, I've already executed cat 0 because I want to show you that the BOM CID is the same. Okay. I just want that to be seen. Hold on, let me check the Spark cluster. Right, so this is the cat 0 Spark cluster. I made it non-ephemeral because we're hacking storage. Let me just record this CID. I'm just putting it anywhere. Well, let's say here. Hold on, my keyboard isn't working. That's not good. Oh, there we go. Okay, so take note of this. Okay. This is the output of the second cat. Just ignore that. Okay, take note of that. Okay, and this, I should just explain this right now. Okay, so this is the CID of this BOM. This is the URI in S3, right? So right now, this BOM is in S3 and it's on IPFS. This is CID of, this is the URI of the uncontent address data. So this data isn't content addressed. This is the invoice, which contains the content addresses of the data in S3. This is a data set of a single partition. So this partition is on IPFS. There isn't an input BOM because this cat is creating the output of this cat is the input for the subsequent cat. So there's no input BOM CID. This log contains like IPFS IPFS URIs which change. Okay, so that's why they're not in the BOM. Otherwise, the CID would change. This is a CID of the infrastructure as code. This is that file on my local machine. Moving on, this is the transformation CID. I think I showed you an example of that. I'm not going to look for that in my IDE, etc. Okay, so that's the most important things that are here. Okay, so let me just re-execute that and show you what's happening. Okay. Okay, right now, the dependencies of the cat 0 application. Okay, right now, the cat 0 application is being packaged into a virtual environment. These dependencies are being installed into that virtual environment as well. Okay. So the virtual environment is created, it's installed in the virtual environment. The virtual environment is zipped. okay? After this virtual environment is compressed, it will be distributed to all the worker nodes in the Spark cluster, okay? Terraform is running, providing the execution for that cat, okay? That's Terraform. Spark is like driving an elephant. It's annoying and it takes time. So, okay, hold on. Hold on, I have to monitor resources, hold on. Okay, now, PySpark has an interface for creating a container that I've taken the Docker file for, modified it to include the IPFS client. This container is being, okay, it's running. Hold on. I can't keep up with it. Okay, Spark logs. I should disable these. Let's see. Spark is slow when your data set is small.
This is true.
Okay. Keep broadcasting, executives. Okay. I should ask. This is a good time for questions. Yes.
Oh, good. Joshua, actually, you know what? Look, it's well said. One question I have for you in particular is when you think about deploying these cats at any scale, the access to the cats, meaning the load balancer or how the user's request would make their way to the cats, does that access path itself need to be content addressed as well? Or do you rely on some other mechanism to distribute and decentralize as best as possible? What do you guys have any thoughts about how to handle that gateway component?
Okay, so cats in this example, which is a proof of concept, the reason why the cat is non-ephemeral is just the storage hack. Cats hasn't been deployed, right? It hasn't been deployed. The only reason why it sticks around is because I don't have storage. I don't have content address storage. So what you're describing is a cat on a mesh network that has been deployed that that requests are sent to, right? That can be used to execute multiple transformations and produce a bomb history. That is her future vision.
Mm-hmm.
Okay, that's a future vision. We've considered, okay, hold on. Wait, I kind of want to answer this. That's a future vision, okay? Actually, you know what? Let me just continue. I will remember this and we will continue this conversation.
Sounds good.
I want to discuss this. Okay. Yeah, I just wanted to show you. Oh man, I forgot to show the data set. Okay. I'll show it in the next one because the input and output are in the second cat. Okay. Yeah, this is an example of things changing. You know, the IPFS client has a different URI, so I just removed it from the BOM and put it in S3. Okay, so let's see. Where did I put that? Oh, yeah, it's the same. Okay, that's good. All right, let me try executing the second cat. That's cat 0 Spark cluster. Okay. This one's kind of funky. This one has a bug. Yeah, okay, I can answer your question. Okay. Yeah, so the vision is kind of like function as a service, right? Why? Because it's the underpinning of multiple kinds of data processing, like batch and streaming. And can be used for IoT, which kind of lends itself to this node concept. So the processor is the software that will go on the node. I guess this is the node, right? So the processor is a software that will go on a node. This is an abstraction of the node. This is like a quantum of the node, right? Right now, I have to say it's a VM because you can't put, it's difficult to put Docker inside Docker, but that's a story for another, it's a story for another time. It is possible, but you know, you have to, I can't tell you that yet.
Well, fair enough. Well, I want to say I really appreciate you guys taking us through a demo because we're all at various stages of building. And so we're all building together and just seeing what you guys are putting together, just seeing some of the raw inside pieces of it is super helpful. So I very much appreciate that.
I'm trying to get through this so I could ask you questions about computer over data. That's what I want to do, but that might not be possible. That's a follow-up. Hold on, sorry. Any more questions while this completes?
Just one last question for you. In terms of workloads, so separate from the computer over data working group, one of the other projects I work on is Baco and we're trying to serve deterministic and non-deterministic workloads, which is tough. Do you guys make any distinction whether it's deterministic and it's always going to return the same output, or do you in this case primarily focus on non-deterministic workloads, just whatever the data says at the time, it's going to be unique and different for each output?
For a strategic implementation standpoint in terms of time, okay, I didn't care about whether or not it was deterministic or non-deterministic. That's up to the user. That there's a way to enforce that, which is on the roadmap. Okay.
Yeah.
And there is a way to enforce that. We know how to enforce that, and we would have to talk again for that. But it's not important for the implementation to prove the concept. This particular transformation is deterministic. So somebody sticks if something changes, I mean, that's up to the user. For the POC, the example is deterministic, but there is a way to ensure that.
Yeah, I think for the purposes of being able to track provenance, immutable data and item potent process is a goal that we'd like to achieve to the extent possible. What do you do to a process that has a random number generator in it? Well, you can get around that by passing a random number in as an input parameter. Something along those lines. To what extent can you make a process? I'd prefer item potent to deterministic, I guess. Same input, same output.
The seed goes in the bomb and the data provenance record entry. That's how you do it. But
I love it.
Yeah. I need leverage to talk to you again, so I can ask you.
Well, don't worry. This does not have to be the last session. We can always have a part 2.
All right.
We're not going anywhere, but this is tremendous.
Yeah, my understanding of data provenance is, hey, we're going to store record. We're going to store all of the data, all of the information necessary to reproduce this if the process is deterministic. Okay. If the process is non-deterministic on the network, that's like a fork, but that can't be managed because it's like, I don't know. There will be cases in which people want non-deterministic processes, but what needs to be, that's something I have to think of. the case for which they want non-deterministic processes. I mean,
Yeah. Yeah,
That's-
we're in the same boat, especially if you look at like a lot of blockchain processing, you know, like popular Ethereum type processing, it's deterministic. It's the same output every time when you run the smart contract. But then in our world of more broader use cases, it's entirely open-ended. So we're always kind of trying to figure out use cases, but we haven't found a strongly deterministic use case either. But it's helpful to hear your guys' perspective
okay,
on
so
that.
I'm sorry about this, but you know, when this you know, this is on my local machine, and you know, I have to determine, you know, I think we use too much resources on my local machine. But the idea is, Kubernetes was used because it's just the backbone of services deployed in, you know, cloud service
Yeah.
provider. I wanted to go as bare metal as possible. If I continue down this route, I will get rid of S3. I'm tired of it. I don't like Spark. Okay. I read, hold on. I mean, do we have any time constraints?
Well, I'll go ahead and wrap up the recording here in just a second, but we can keep going ourselves as well. So I'll just go ahead and hit pause right now and we'll be good. And then